Hi everyone, welcome back. Today we're going to be talking about Introduction to Database Design, and we will be getting into the specifics of functional dependency theory. So as a brief introduction, you know that you have data, and there are different ways in which you can split and combine tables. There's different ways to partition the data for storage and for ease of access. But how exactly do you pick a schema? How do you know which one is better? How do you know what better means? Fortunately, there are going to be some principles that'll guide us in making these decisions and help us improve in this space. So if we consider the following set of schemas, so we think of students, for example. So we can think of a university database, and students have a UTOR ID, they have a name, they have an email address. Do we want to leave it in one table, or would we rather split it up into two tables? For example, students, UTOR ID and a name, emails, UTOR ID and an address, as in an email address, which can be joined together based on some key. In this case here, it's the UTOR ID. What about if we look at something a little bit more general? For example, home ownership, so house ownership or property ownership. A house has a street, a city, a value, an owner, and a property tax amount. Well, do we want it in one table, or do we want that split up? What helps us make these decisions? Why would we pick one over the other? How does it work? And then if we think a little bit more futuristically, well, how exactly do we tackle this problem as we scale? So we have to consider scalability in mind as the data set grows. Is this something that's going to be frequently accessed? And we have to also consider the fact that, for example, constraints, well, they can be domain dependent. So one big thing here is we want to avoid redundancy. If we look at this table, we see a name, an address, a beers liked, a manufacturer, and a favorite beer. Well, do we really need to store the manufacturer with the name of the beer? Is that something we want to do? We already know who the manufacturer is. Do we want that type of data repeated here? Would we rather split it and put it into a different table, so partition it, or do we want to keep it the way it is? Now we have to consider a few different things. We have to consider the idea of anomalies. What happens if we update a certain data set or a specific record? What happens if we delete or insert a specific record? How do we know that it updates all instances or deletes all instances? How do we know that on an insertion it inserts and then modifies instances that might have, for example, a different manufacturer or a different address? Database design theory allows us to improve these schemas systematically, but the general idea here is twofolded. The first is to express constraints on data, and the second is this idea of using the ability to decompose the relations to better our understanding of the information. Ultimately, getting a schema in a normal form, so normal meaning conforming to a standard, getting it into a normal form usually means we're guaranteeing good properties. And depending on the type of normal form for the specific scenario we're in, will ensure certain properties being upheld. For example, not having any anomalies. We'll talk about other things like dependency preservation later, but not having anomalies is a good start. The process, the formal process of actually converting a schema to a normal form is called normalization, and we'll be talking about this today. So let's start with part one, and part one is functional dependency theory. So given a functional dependency, for example, we read a statement like X implies Y, holds in R. So given some relation in R, X implies Y. So some attribute X implies some attribute Y. What this actually means is that X functionally determines Y, or Y is functionally dependent on X. And that's an important term to understand. X needs to be there for Y to exist. So a couple of things you'll notice in these slides in terms of conventions. X, Y, and Z will represent attributes, whereas A, B, and C will represent single attributes. So X, Y, and Z, set of attributes, A, B, and C, single attributes. Also, no braces are being used for sets of attributes, just A, B, C, rather than this specific notation you see here, A, comma, B, comma, C, within squiggly brackets. So why functional dependencies? Well, the word functional is there because there is a mathematical function that takes the values for X and gives them some unique value for Y. You can think of it just like a hash function, same thing that exists here, or any mathematical function. Given that X, you get some unique Y. Dependency because the value of Y is functionally dependent. It's dependent on the value of X. So that means X will actually help you infer what Y is. And that's important. Knowing that's important, but also preserving that as we decide to split and combine data is important. So if we need a special type of constraint to help us with normalization, for example, we're working with X implies Y, or Y is functionally dependent on X, that's an insertion. So that's an assertion made on our relation R, on our table. And whenever two tuples of R agree on all the attributes in that set, they also must, so in that set X in this instance, they must also agree on all attributes in that set Y. So if we look at an example here, R, so our relation R that has A, B, C, you'll notice that if we say that X equals A and B and Y equals C, the combination of the attributes that exist in our first two columns, A and B, will help us determine what actually exists in C. So there's some level of inference. Now, there are properties that actually will allow us to direct functional dependencies and work within this space. First, there's rules. So a couple of rules are trivial functional dependencies, the ability to split and combine them, as well as Armstrong's axioms, and you will have seen this in your discrete math courses. They carry over here, so they propagate into this space in databases as well. And the second is this idea of algorithms that are related to functional dependencies, some of which are closure and minimal basis of a relation. So we'll talk about closure in more depth. Minimal basis will be provided in a supplementary document. So if we look at the rules, specifically trivial functional dependencies, well, there's a couple things that can be said here. The first is that not all functional dependencies are useful. So for example, A implies A, well, that's something that'll always hold. So A can't be functionally, well, technically it can be functionally dependent on itself, but it's something we don't need to explicitly denote. Then something like ABC inferring A, well, we know that we have A on the left-hand side. A infers A. It's a trivial functional dependency. It always holds. Not something we need to explicitly denote. There are other things too. For example, if we have a functional dependency with an attribute on both sides, something like ABC infers AD, as in here, well, we don't actually need to denote explicitly that it infers A, because if we have A and or B and or C, well, in this case here, we know that because we have A and B and C, it infers A. It also infers B and C, but that's not something we need to explicitly denote. So that's something we can consider. We can reduce it to just A, B, C infers D. The other thing we can look at here is deleting them. So the idea here is we split them. So A, B, and C is split into A, B, C, infers A, and then infers D. And that just results in our removal of that trivial functional dependency. Now, these splitting rules and combining rules are pretty straightforward. What you'll notice here is that on a split or on a combine, there's different ways to look at them. One thing we often try to do, because it makes things easier, is to reduce things to what is known as their singleton form to get it down to a singular attribute. So for example, if we look at something like this X, and X is just a set of attributes A1, A2, A3, so on to AN. It holds for R exactly when we say that X infers A1, X infers A2, X infers all the way to AN. That's something that's held for R, for our relation, for our table. So if we have something like this, A infers B and C, we know that it can be split, and we can say A infers B and A infers C. Same thing with combining. So if we know that A infers F and A infers G, well, that's equivalent to A inferring FG. So this is something we can do. We can split and combine. It's a rule that exists. It will become useful once we work within the space of the algorithms, more so with actually with both closure and with minimal basis. One thing to note, it's very important, it's that there's no splitting of the left-hand side. So if you say that these attributes A, B, and C infer D, E, and F, well, you can't then say A and B together without the use of C can infer, for example, D, E, and F. And you can't say that C alone can infer D, E, and F. No, only the combination of the entirety of the left-hand side allows you to infer the right-hand side. And functional dependencies in general are usually expressed with singleton right-hand sides. Makes things a lot easier to work with, especially once we work with closure. So if we look at an example, a running example of drinkers, so drinkers have a name, an address, beers like the manufacturer, and a favorite beer. It's reasonable to assert here that if you know the name of the drinker, you will then be able to infer their address and favorite beer. You can think of name as being a unique identifier. This functional dependency is the same as splitting the right-hand side. So splitting it to name infers address and name infers favorite beer. Another thing that's reasonable to assert here is once you know what the beer name is, so what the beer's liked is, you'll be able to infer who the manufacturer is. And what you'll notice is usually the left-hand side has some strong, unique element to it, which is why they're often candidate keys. So if we go back to that example we had before with our drinkers table, so we have name, address, beers like, manufacturer, and favorite beer. If we know that name infers address, you'll see something like Janeway, knowing what the name is, will infer the address Voyager. Just like Spock will infer the address Enterprise. Knowing the name, again Janeway, will allow you to infer the favorite beer, so Wicked Ale, and beers liked inferring the manufacturer. So knowing that it's Bud means that you know the manufacturer's Anheuser-Busch in this case, AB. Now there are rules that work within functional dependencies, and they're what are known as Armstrong's axioms. So there's 5 of them. There's reflexivity, augmentation, transitivity, union, and decomposition. You will have seen them in discrete math. Here are the rules for you. Same idea and principles apply. Now, with respect to transitivity, so transitive properties, if you consider some type of a functional dependency, for example, A infers B and B infers C, then we know that A infers C holds. So if we consider another functional dependency, AD infers B and B infers CD, we know that AD infers CD. Or alternatively, you could just reduce it to AD infers C, as we have D on the left-hand side. There's no reason to explicitly write it on the right-hand side, so that's a reduction based on the trivial functional dependency. Now this leads into a really interesting topic, which is how exactly do you find or identify functional dependencies? Well, it turns out DBMSs actually can't do this for you. It's something that you, or your DBA, based on domain knowledge, has to come up with the features intrinsic to the data set to determine what your functional dependencies are for your specific use case. So it's something that you know or you can reasonably assume about your data, but it's not something that can be automated for you, at least not easily or yet. Everything's technically possible. Now, database engines themselves, because they can't identify those for you, it's really important you get them right from the get-go. It's something that your architects, your designers, your DBA will work together to determine what they are. The other thing here that's really important to consider is the fact that your DBMS can't even optimize those functional dependencies. It only has a finite sample of data. You're giving them, you're feeding it in what they are. So that's something that it needs to work on. It's something that it's going to be constricted or bound by based on your decision. Now, FDs themselves are a generalization of the idea of keys, which is why I sort of alluded to the fact that they're usually a candidate key. They're really often just a super key in even more general form. So a super key, something like X infers R. Well, a super key must include all of the attributes of the relation on the right-hand side, also short formed as RHS in capitals. A functional dependency, something like X infers Y. Y is functionally dependent on X. It means that a functional dependency can involve just a subset of the key. So for example, we look at that house example where we had a street, a city, a value, an owner, and a tax amount. Well, if we know that our functional dependencies say street, comma, city infers value, owner, and tax, and city, comma, value infers tax, well, we're working within two spaces. Or we're working in the first one saying that it's both a functional dependency and a key, whereas in the second example, it's just a functional dependency. And we have to keep this in mind. Now, when we look at inferring functional dependencies, so given a set of functional dependencies, it's actually possible to infer even more functional dependencies. So we can continue sort of down a chain. And this helps because we have the domain knowledge and we often are able to make those connections. So if we assume, for example, x1 infers a1, x2 infers a2, all the way down to xn infers an, well, does the functional dependency then y infer b also hold in any relation? Well, what we need to do, given any functional dependency that we're trying to see if it makes a connection, to prove it, we actually must assume that two tuples agree on all attributes of y. And there's a couple of things to consider here. One is the general space. So in general, does it hold? The second thing to look at is, based on our data set, is that something that should hold? So are we confining ourselves to the current data set, or are we combining ourselves to a general space? Often they're one and the same, but that's something we need to distinguish from the get-go. So let's look at an example here. If A infers B and B infers C, we know that A infers C holds through transitivity. So A infers C is then entailed or implied by the set of functional dependencies A implies B and B implies C. But this allows us to play with something. It allows us to play with the fact that if we know that this is the case, if this is something that can be inferred, well then we have the ability to split these up. We can join two tables, one that has the columns A and B, another one that has the columns B and C, based on the common attribute B. We can naturally put these tables back together. If we look at a big example like this, so we have, it's an insurance example that has client IDs, their level of income, products they may have or other products they may have, a rate of return on potentially investments, the country they belong to, the city, and the state. Well, if we say that one of our functional dependencies is the combination of income and other products, which infers their rate, so income, comma, product or other product infers rate. And we say that country, comma, city infers state. Well, we have a little bit of an issue here. So USA, San Francisco, great. But are we talking about the San Francisco in California, or are we talking about the San Francisco that's in Maryland? How do we know which one it is? Did we consider the general case in this instance? How do we actually prove that generalized case? And that's sort of difficult, but it's something that can be visually perceived. Now, formally what we use is what's known as an algorithm called the closure test. So the closure test is for a set of functional dependencies given some attribute set Y and functional dependency set F, and you can denote them as Y subscript F superscript plus to denote your procedure of closure. So plus meaning gaining, so we're gaining to see how many combinations of functional dependencies can we put together to see if we get back what we started with on a split. And we have the ability to actually compute this closure. So this is the algorithm. Now, let's look at this in a general sense. If we compute the closure of Y, given an attribute set Y and a functional dependency set F, we know that we are trying to see if it encompasses some set. So given any functional dependency that makes some inference, can we get the closed set in which we started with? So I'm going to back up for a second. When we think of this generalized idea, we need to figure out how do we actually combine things and how do we split them. So we have a set of data. We've decided to split it in a certain way. So we've created tables, division of attributes. How then do we put them back together to make sure our data is whole, so without having issues, without having anomalies? More so than that, when we deal with functional dependencies, how do we make sure that we split these tables so that we're upholding these functional dependencies that exist within the data, but at the same time, when we combine them back together, how do we make sure that those functional dependencies remain whole? There are no errors in the functional dependencies. There's no loss in those functional dependencies. We're able to put them back together. How do we do that, and how can we check that? And that's through this algorithm of closure. So if we have, for example, a relation R with the attributes A through F, we have the functional dependencies AB infers C, AC infers D, C infers E, and ADE infers F. Well, we need to start with somewhere to see one of the functional dependencies to see if we can get back our entire set. So if we look at one table, we look at this table in the top left-hand corner, we see that, okay, with the attributes A and B, we're able to obtain the attribute C. So now we have A, B, and C. Through the second functional dependency here in red or maroon, we have AC infers D. So now we have A, we also have C, we can infer D. So we know we have A, B, C, and D. Through the third functional dependency in green, C infers E, we know we have C at this point. We can infer E. So now we have A, B, C, D, and E through this functional dependency. And the fourth functional dependency says with A, D, and E, which at this point, once we've combined them, we have it. We have A, we have C, we have A, we have D, and we have E. That allows us to infer F. And thus, through proving this, through going through these steps of closure, we have the ability to then say that AB is in fact a candidate key, which is incredibly neat. We have the ability to use these functional dependencies to determine if something closes our set. With that combination of attributes that we started with, A and B, we were able to obtain all the other elements, all the other attributes that exist within our data set. Because of this, we can therefore definitively say that it is a candidate key in our set. And we can repeat this for every functional dependency to see if the rest are also candidate keys. So this is just another example in terms of closure and how you can denote it. For example, when you look at a key A, so for example, if you're trying to determine if it is a key, you look at your attribute A, you go back to your functional dependency set. A allows you to infer D, A and D together allows you to infer E. Now you have A, D, and E. Is there anything else you can infer? No, because you don't have B and you don't have C. So you know that the closed set here only allows you to infer A, D, and E, so itself plus D plus E, just with A. And you can repeat that for AB, you can repeat that for AC, you can repeat that for B, and you can repeat that for D to see what allows you to obtain an entire closed set. In this case here, it's A and B, as well as A and C. So these two options, or these two attributes combined, allow you to infer the entire set of attributes. And because of this, we know that this is a fully closed set. Therefore, A, B, and AC are candidate keys in our relation.